All right, welcome to Physics Video 3.6. We're going to be learning today about what are called free body diagrams and normal force. So your objectives are along those lines. By the end of the video, you should understand how to draw a complete free body diagram and explain what a normal force is and understand when there is a normal force acting on an object. All right, so free body diagram is just a drawing of an object with all of the forces on the object labeled at one specific instant. I want to emphasize this. Usually your drawing is going to be just one specific instant. So the drawing also will include the following information written off to one side. You're going to write down what the net force is, you're going to write down what the acceleration is, and then you'll write down what the velocity is at that instant. And occasionally, if we're solving a problem, I might write down the initial and final velocity also. So anyway, we've already made drawings like this, but so far all the examples that we've done have only had horizontal forces since the objects were being pushed horizontally. And as a result, since the motion was horizontal, we didn't need to worry about vertical forces. However, in the real world, we almost always have vertical forces because we almost always have gravity. So here's what we're going to do. It says there's some definitions here. There are not. Here's the general process for making a free body diagram. It's basically 3 steps. Your first step is to draw the object and then identify the following things. You're going to write down what the mass is. Remember, you're going to write that inside the box and figure out what the weight is. The weight is going to be drawn as an arrow pointing down, indicating that gravity is pulling this thing down. And what will happen is in most problems, I'll give you either the mass, in which case you'll have to calculate the force of gravity, or I'll give you the weight, the mass, sorry, or I'll give you the weight, comma, force of gravity, and you'll have to find the mass. So I'll always give you either mass or weight, and you got to find the one that you're missing. All right, so that's your first step. Draw your object and label those 2 things. Second step is label any forces that are given. You know, maybe it'll say Roy pushes the box with X amount of force, or there's a force of, friction of 10 newtons or whatever. Draw those. All right, and then the third step is the one that always tangles people up. It's this. You got to stop and think about what you know. All right. If you know the acceleration, then you're going to use Newton's second law to find the net force. And then usually at that point, what you'll need to do is you'll need to find some missing force. So the idea is if you know what your net force is, and you're missing, for example, force number 2, you can solve for it. All right. As a quick reminder, too, remember that if the object isn't moving or if it has a constant velocity, that's going to make your acceleration 0. All right. Now, the other possibility is that sometimes you won't know the acceleration. You won't be able to figure it out. And in that case, what will happen is you'll know all of the forces on the object. So in that case, you'll use the definition of net force, which is this guy. So you use the definition of net force to find the net force. You'll add up all your forces. And then you'll use Newton's second law to find your acceleration. Okay? So it's probably worth your while to go back and watch that slide again. Because I'm not, yeah. Okay, sorry. I'm not feeling 100% this morning. Okay, so probably the easiest way to do this is to jump in. Here we go. So example number 1, we've got a 6-kilogram cat named Gordon who is jumping out of a tree. So you need to make a free body diagram of the cat while he's falling. So draw yourself a cat. You can either just draw a circle or a box, or if you're feeling artistic, you can draw an actual cat. So there we go, cat. All right, so step 1, draw the object. Identify your mass and your force of gravity. Oh, I don't know the force of gravity. I'm going to calculate it. So somewhere off to the side, figure out what your force of gravity is. For most of you, you probably don't have to write this out because it's just 6 kilograms times negative 10 meters a second squared. But I do want to emphasize the fact that, technically it's something that you're calculating. You don't know it, right? So your force of gravity on this one is negative 60 newtons. Okay, so that's step 1. Identify your mass and your force of gravity. Step 2 is identify any given forces. So if you read through the problem, a 6-kilogram cat named Gordon jumps out of a tree, make a free body diagram of the cat while he's falling. There aren't any any forces described in the problem. It doesn't say, you know, Roy pushes it or friction is or anything like that. So step 2, there's nothing to do. Third step is think about what you know. In this one, actually, you can go a couple of routes. Option 1 is you can say, oh, well, we know the net force because the only force is the force of gravity. So our net force is just going to be negative 60 newtons, right? And then find your acceleration by doing net force over mass. And we hopefully already know what the answer is, right? There you go, right? You could have flipped that around. You could have said, oh, well, I know it's falling, so I know the acceleration is negative 10 meters a second squared, and then done mass times acceleration to get your net force. Either way, there you go. There's your drawing. So your completed drawing, here's the deal. Your completed drawing should have this. Your drawing with all of the forces. You should write down what your net force is. So this is part of my drawing, part of my free body diagram, and you should have your acceleration written down. Okay? In this one, there's really nothing that I can say about the velocity because it says he jumps out of the tree, so I don't know what his initial velocity was because I don't know how fast he jumped. I don't know how fast he's moving at this instant, so I'm kind of done right there. All right? So let's do another one. All right, this example is about Roy holding a 14-kilogram box in his hands. All right, when you make a free body diagram, the reason it's called a free body diagram is you're drawing just the one object. Okay, so in this problem, we're drawing a free body diagram of the box. And I probably should have said that up here when I said make a free body diagram. It's of the box that we're making the free body diagram for. Okay, so here's the box. Start by identifying your mass. Calculate your force of gravity. I'm not going to write it out. It's just 14 times negative 10. Gives you negative 140 newtons. Okay, so that's step 1. Step 2 is identify any given forces. It doesn't give us any numbers here. It sort of alludes to the fact that Roy is going to be pushing it, right? Because he's holding the box. He's going to be pushing it. But it doesn't give us any numbers, so I'm not going to draw that yet. All right, so for step 2, there's really nothing to do in this one because there aren't any given forces. All right, so step 3 is the think step. And so the first option is if you know the acceleration. So do we know the acceleration? Well, what's the box doing? It's just sitting there, right? It's not moving because Roy's just holding it. So in this problem, the acceleration of the box is 0, which means, oh, Newton's first law tells us that means the net force has got to be 0. So that means that, let's see, our net force in this problem is the force of gravity plus, we already said Roy had to be pushing it, right? So those are only 2 forces. We know our net force is 0. We know our force of gravity is negative 140 newtons. So what does the force of Roy have to be? Well, if you add 140 to both sides, that's got to be your force of Roy. Basically, all you're doing is you're saying gravity's pulling this down with 140 newtons. So Roy must be pushing it up with 140 newtons to prevent it from falling, right? So there's your free body diagram. We can also write down what the velocity is, right? Velocity is 0 because the box is not moving. All right, so here is my completed free body diagram. Okay. Next example. 14-kilogram box sits at rest on a table. All right, there's some information down here. Ignore that for a minute. I'll explain that in a second. Okay, so we've got a box sitting at rest on a table. It's still a 14-kilogram box. For all intents and purposes, this example is the exact same thing. We've got a 14-kilogram box. Gravity is going to pull it down with a force of 140 newtons. It's just sitting at rest. So once again, our acceleration is going to be 0. Our net force is going to be 0. So the difference, though, is this time, instead of having a force of Roy holding it up, Roy's not touching it. It's just sitting on a table. All right. So in the last example, Roy is what was preventing the box from falling. In this problem, it's the table that's preventing the box from falling. So the force of the table up here is 140 newtons. All right. So why did I do this example if it's the same thing? Well, one, it illustrates the fact that stuff can push stuff, as I've said before, right? This time, we've got the table pushing the box, which sounds weird, but that's what's going on. And then secondly, we're actually not going to call that the force of the table. We are going to call it the, we're going to call it the normal force. All right, so anytime you have a support force provided by a table or any sort of inanimate surface, oops, I missed a parenthesis here, that's called normal force. Okay, so instead of calling this Ft, we're going to call it Fn, which stands simply for normal force. Okay. Cool. There you go. So let me jump back for a second. In this example, it is a true statement that the force of gravity and the normal force are equal, right? They're both 140 newtons. All right, that doesn't always happen, which is the point of this next example, which is mislabeled. This should be example B. Okay, so we've got a raccoon. Since we're running tight on time, I'm going to just draw a box for our raccoon, 12 kilograms. Gravity is pulling the raccoon down with a force of negative 120 newtons, right? Just 12 times negative 10. All right, so that's our step one, mass and force of gravity. Step two, any given forces. Oh, there's something going on here, right? Sally pushes him down with a force of 50 newtons. So put in your force of Sally, 50 newtons, right? Okay, so imagine this. You've got an object sitting on the ground. This happens to be a raccoon, which doesn't affect the problem at all. And you push it down. What is it going to do? All right, so we're on to our step three now, where you've got to think. All right, now, a lot of times people look at a problem like this and they go, oh, well, the raccoon is being pushed down. It's going to move down. But no, it's sitting on the ground. If a box or a table or a raccoon is sitting on the ground and you push it down, it's not going to move. So automatically we know our acceleration is 0 and our net force is 0. All right? So why isn't it moving down? Well, because the ground is supporting it, right? So there must be an upwards force from the ground. It's an inanimate surface. I'm going to call it the normal force. And the question is, how much force? So some of you are able to look at this and just go, oh, well, you've got to cancel out the two downward forces. You've got 120 newtons pulling down, 50 newtons pulling down. That's a total of 170 pulling down. So the normal force must be 170, which is correct. For some of you, though, you might want an equation to do it. So here's the equation. Your net force is the force of Sally plus the force of gravity plus the normal force, the force of the ground, right? And put in your numbers. 0 equals your force of Sally is negative 50. Your force of gravity is negative 120 plus your normal force, and solve it. So you get 0 equals negative 50. No, sorry. Negative 170 plus your normal force. Add the 170, and your normal force comes out to be 170 newtons. All right? So basically, you guys, what's happening here is your normal force is exerting just enough force to prevent the object from moving down through the surface, right? It's preventing the raccoon from moving down through the ground. All right? And I think I forgot to do this on my last example. The raccoon is not moving, as was the case with the box in the last example. So write down your velocity. Here is your completed free body diagram. All right, I have one last example, if I remember correctly, and then we're going to stop there for today, and we're going to do more free body diagrams later on, but I wanted to focus on normal force today. Excuse me, I'm sorry. All right, so this last one, we've got a walrus. Okay, so can I draw a walrus? Walruses have mustaches. All right, so there's my walrus. I'm actually pretty happy with that walrus. Should you be happy? You should. No, that just ruined it. All right. Sorry, I'm wasting your time while I'm drawing. I'm sorry. Okay, there we go. All right, so we've got a 300 kilogram walrus. Write down your mass. Put in your force of gravity. This one is super important, so I am going to go over my 15 minutes. Please make sure that you get this last example down. This will be the last one. Okay, so gravity's pulling the walrus down with a force of 3,000 newtons. Roy is going to try to lift the walrus. All right, so here's our step 2. Write down any given forces. So there's a force of Roy, right? 500 newtons, right? So now we're on to our step 3, which is think. So, are these all of the forces? Well, I don't know. We got to kind of think about this. Let's see. Roy is lifting up with 500 newtons on something that is being pulled down by gravity with a force of 3,000 newtons. So think about that logically. Does it make sense that this 500 newtons would be enough to lift a 3,000 newton walrus? No, that's not enough force to lift him, right? Okay, if I left it like this, my walrus would be moving down, wouldn't he? Because I've got more force pulling him down than I've got lifting him up, so he'd be moving down. But we know he can't be moving down because he sits on the floor, right? So the walrus isn't going to move. There's going to be a normal force, right? So what do we know? We know the walrus isn't going to move because 500 newtons wasn't enough to lift him. Our acceleration is 0. That means our net force is 0. Write it down while I'm thinking about it. He's not moving, so the velocity is 0. All right, so now we got to find our normal force. Well, some of you are able to do this just by thinking about it. We've got 3,000 newtons down and only 500 newtons up, so the normal force needs to fill in the difference, right? Mathematically, it's this. Once again, net force equals force of gravity plus force of Roy plus force normal force, and plug in your numbers. Net force has got to be 0. Gravity is negative 3,000 newtons. Force of Roy is 500 newtons plus the normal force. So you get 0 equals negative 2,500 newtons plus the normal force. Add 2,500 newtons, and you discover that your normal force in this problem is only 2,500 newtons. And basically what's happening here, you guys, is Roy, by lifting up with 500 newtons, has taken some of the weight off of the ground, right? And so, as a result, the ground only needs to provide the extra 2,500 newtons to prevent the walrus from falling. Okay? So here is my completed free body diagram. These are going to take you guys some practice. These are not easy. So we're going to spend a couple days on these. And each day we'll add in sort of a new element to the problems. But this normal force seems to be the one that people have the most trouble with. So I, again, want to caution you about some common misconceptions people make, and then I will stop. Number 1, please remember your force of gravity down here. You got to calculate, right? It's not just negative 10 meters a second squared. All right. Secondly, after you've got your force of gravity, if the object is sitting on a surface, if it's physically not moving off of the surface, there's going to be a normal force, which may or may not equal that force of gravity. Okay. Sometimes the normal force here equals the force of gravity. Other times, not so much, as is the case here with our weird-looking walrus. All right, so there you go. Free body diagrams and normal force.